Hi everybody, I hope this video finds you well. In today's video, we're going to be moving on into Chapter 5 of your textbook, starting with Section 5.1 here, and discussing sort of a little bit of an extension of the concept of a vector space that we've been dealing with for quite a while now, and extending that to what is called an inner product space. We're going to go through the sort of general definition of what it means to be an inner product space in just a moment. Then we'll go ahead and talk about, even though it sort of has this fancy name, inner product space, a common inner product that you guys have already encountered, which will turn out just to be the dot product in Rn. Then we'll look at some more interesting inner products that work for other vector spaces, specifically an inner product that works on the vector space for functions, and also an inner product that works for vector spaces with matrices. So we'll take a look at a couple things like that. All right, so let's get right into our definition here. We've got V, a real vector space. So everything we're going to be doing right now is going to be for sort of real vector spaces, meaning that the scalars are all real values. Your book also discusses how to do all of this inner product stuff for complex vector spaces as well. We won't really need that for our course, so we won't be covering that. Whenever we talk about an inner product space, we're always going to be talking about the real version of it, not the complex one. So an inner product is simply a function that takes as inputs a pair of vectors and outputs a scalar value. And it is written as sort of brackets u comma v for u and v as vectors. And to be considered an inner product, it has to satisfy these four properties. Before we start to discuss those four properties, do just keep in mind what an inner product is doing, right? An inner product is taking in two different vectors, so two vectors from your vector space, and it outputs a value, just a scalar value. Okay, so what are the four properties that must be satisfied to actually count as an inner product? Well, the first one is that the inner product of a vector with itself always must be greater than or equal to 0. So in other words, whenever you do an inner product with a vector with itself, you must always get a non-negative scalar. Furthermore, the only vector whose inner product with itself equals 0 is the 0 vector. So in other words, what this statement is basically saying is that when you perform the inner product with a vector and itself, you have to get a non-negative value, and the only time you're allowed to get a 0 is if the vector that you are doing that inner product with is the 0 vector. So only the 0 vector has its own inner product as equal to 0. All right, the other properties are a little bit simpler. First, the inner product of v and u is the same as the inner product of u and v. So in other words, inner products must be commutative. So this is just a commutative property here. Okay. They also have a sort of scalar property. The inner product of k times a vector v with the vector u is the same as the scalar k times the inner product of v and u. Now, the interesting thing you should note here is that that scalar multiple is only on one of the vectors, and you can pull it outside. So that tells you that it doesn't have a traditional distributive property. If you were to distribute that k back in, it doesn't go on both. It would only go on that sort of lead component. Now, since we do know it's commutative, you could actually have it go on to either one. You could have it distribute to v or distribute to u, but you can't have it distribute to both. Finally, we have what is considered a linearity property. The inner product of u plus v with another vector w is the same as the inner product of u and w plus the inner product of v and w. So in other words, it's linear in a single component. So if you have the same thing you're inner producting with, in this case w, then you can go ahead and add that u and v. All right, so if you define this operation or this function and it satisfies these four properties, then you have what is called a real inner product space, right? So you take your vector space and you define this extra operation, it makes it a real inner product space. One other quick definition: if you have a real inner product space, then the norm of a vector, which for some of you guys, if you've taken like geometry or physics classes, norm is the same concept as magnitude. So the norm or magnitude of a vector in a inner product space is given as the square root of the inner product with that vector with itself. So the norm or magnitude of a vector is defined as the square root of the inner product of the vector with itself. Okay, so this definition of an inner product space is very general, just like we sort of generally defined what it means to be a vector space. The first thing we're going to talk about is the fact that the most common inner product that is out there is one that you guys have already encountered. It's the dot product. So let's go ahead and talk about that. So this is what sometimes referenced as the standard inner product on the vector space Rn. So the standard inner product for Rn is the dot product of the two vectors. And if it's been a while since you've seen dot product, remember all that means is that if you have vector v being v1, v2 through vn, and vector u is u1, u2 through un, then the inner product of v and u is defined as v1 times u1 plus v2 times u2 all the way down to vn times un. So you basically multiply the components and then sum all that up. Now, if from like 220 multivariable calculus, geometry, physics classes, you guys probably know quite a bit about this particular inner product. It is an inner product in the sense that it satisfies those four properties. You guys can go ahead on your own and verify that this operation here does satisfy the four properties of an inner product. Your textbook also goes through that proof and shows you that it really does have all the properties that are needed. I think you guys have probably already been exposed to a lot of stuff about the dot product, so we won't go ahead and do that. Instead, we'll just do a couple examples with this and then move on to some more non-standard inner products. So really quickly, just as an example here, let's use this standard inner product for R5, and we're going to define the vectors v to be 1, 3, negative 1, 0, 2, vector u to be the vector 3, 1, 6, 5, 0, and vector w to be the vector 1, 0, negative 2, 3, 1. We're going to try to just calculate a couple things. First, the inner product of v and u, and we're going to calculate the magnitude or norm of w. So let's go ahead and do that. So the inner product of v and u, well, what we're going to do is we're going to multiply component-wise and then add all that up. So we would do 1 times 3, and then plus 3 times 1, plus negative 1 times 6, plus 0 times 5, plus 2 times 0. Then if we were just to start actually doing that arithmetic, we get 3 plus 3 minus 6 plus 0 plus 0. And if you sum all that up, you would get 0 there. So the inner product of vector v and vector u would be 0. Now I want to make two comments here. First of all, you might say, well, doesn't that violate one of the rules that we sort of said, that the inner product of a vector with itself can only be 0 if the vector is the 0 vector? Well, remember here, we didn't do the inner product of a vector with itself. We did the inner product between two different vectors. That can come out as a positive number, a negative number, 0, whatever you like. That first property, just let's go back and take a look at it. That first property is about the inner product of a vector with itself. That is guaranteed to have to be non-negative and can only be 0 if the vector is the 0 vector. But for inner products between two different random vectors, you can get any sort of number you like. The second comment I want to make here is that you guys might remember from your sort of standard work with the inner product or with the dot product that when you get a dot product of 0, what this basically means is that geometrically, vector v and vector u are orthogonal vectors. They actually are formed at a 90-degree angle. And actually in section 5.2, we're going to extend the concept of being orthogonal to vectors in general, not just geometric vectors, but we're going to actually expand that concept to saying that whenever, no matter what inner product we're using, whenever the inner product of two vectors is 0, that means that they are orthogonal. Okay, let's go ahead. That was A there, so let's go ahead and also do B here. So we know that the norm of W is the square root of the inner product of W and W. So then that would be the square root. So we're going to do the inner product of W with itself. So looks like that would be 1 times 1 plus 0 times 0 plus negative 2 times negative 2 plus 3 times 3 plus 1 times 1. Okay. And the square root of that whole thing. Keep in mind that the norm or magnitude of a vector is well defined because by one of the inner product properties, we know that the inner product of a vector with itself is always non-negative, so square rooting it should always be fine. Okay, so now we have square root. We get 1 plus 0 plus 4, looks like plus 9 plus 1. And looks like that should again give us, this guy has a norm of square root of 15. So the norm or magnitude of vector W in this inner product is the square root of 15. Now, this is just to sort of give you guys a little bit of just practice, sort of reminding yourself about the dot product and also just some notational stuff here. But one thing I do want to mention is that while this is the standard inner product for Rn, it is not the only one. You can define other inner products, right, that have different sort of operations that do follow those four properties that still work for this vector space Rn. And actually, if you look at some of the suggested exercises, or I believe even on one of the take-home quizzes, you'll actually see a non-standard inner product defined for Rn, and you get a chance to sort of work with that. For now, though, in this video, we're going to move on to not talking about different inner products for Rn, but talking about an inner product for a completely different vector space in general. In other words, we're going to try to extend the concept of an inner product to vector spaces that have vectors that are functions. So let's go ahead and talk about how to do that. So it turns out that a very common inner product for functions, this can be used when you're working in those polynomial spaces or in any of the spaces of like continuous functions or functions that have infinite derivatives or anything. Notationally, I just wrote C0 of R, which is the set of all continuous functions. But keep in mind, inside of the set of all continuous functions are all the ones that have one derivative, two derivatives, all the way to an infinite number of derivatives. So you can use this inner product for any of those sort of functional vector spaces. So how do you use this inner product? Well, a common way is you say, let f of x and g of x be elements from one of these vector spaces. Then we define the inner product of f of x and g of x as the integral from a to b of f of x times g of x dx, where a and b are any choice of constant. So you can do this for going from any value to any value. Now, in your textbook, and I think it's definitely worth reading, they go through and they show that this thing really does satisfy the four properties of being an inner product space. Now, I do think that that's a really important derivation, but I'm not going to repeat it in this video because it is laid out in your textbook. When we talk about our inner product for matrices, will get a chance to go through and verify the four properties, so we'll get to see an example of that. But I highly recommend reading the one from the textbook, proving that this type of inner product really is an inner product. All right, but for us, let's go ahead and jump right in to looking at an example of this. So we're going to use the inner product defined above, this guy right here, with a being -1 and b being 1. Again, because it doesn't matter the choice of a and b in terms of making it an inner product. And we're going to do that on P3 of R, so the polynomials of degree 3 or less. So here's a couple polynomials of degree 3 or less. We're going to let P of x be x squared plus x minus 1, Q of x be x cubed minus x squared, and R of x be the square root of 7/2 x cubed. This seems nicely contrived, square root of 7 over 2. That's probably chosen for some specific reason we'll see in a moment. But let's go ahead and calculate the inner product of P of x and Q of x under this inner product, and also the magnitude or norm of R of x in this. So let's go ahead and take a look at this. So for A here, if we do P of x and Q of x according to this, what we will need to do is we will need to integrate from -1 to 1, again, just because that's what we were told to sort of use here. And then we will need to take the product of our two functions. So x squared plus x minus 1 and x cubed minus x squared. And we'll be doing that dx. So keep in mind that this is a definite integral. So when we actually do this, it will come out as a scalar value, which is what has to happen when you're doing an inner product. So we can go ahead and do that, -1 to 1. I guess we'll need to sort of FOIL this out. Looks like we should get x to the 5th plus x to the 4th minus x cubed, minus x to the 4th minus x cubed plus x squared dx. And it looks like if we integrate -1 to 1, that should be x to the 5th minus 2x cubed plus x squared dx. And if we integrate that real quick, everything should be pretty easy because it's all just polynomials. Looks like we get something that looks like that from -1 to 1, just a bunch of power rules. Then if we plug in, looks like we should get 1/6 minus 1/2 plus 1/3 minus 1/6 minus 1/2 minus 1/3, because obviously when you plug in the -1 into these guys, well, these are even exponents, so it won't change anything. But when you plug in that -1 into here, it will make that a minus 1/3. So this guy will cancel with that. This guy will cancel with that. And it looks like we get 1/3 minus -1/3. So this guy comes out overall as 2/3. So the inner product of this and this is equal to 2/3, right? And remember, when you take an inner product of two different vectors, you can get any sort of value, positive, negative, 0, whatever, right? In this case, we got 2/3. Main point, though, is that this inner product does yield a scalar value there. Okay, let's go ahead and do part B as well. We'd like to calculate the norm of R of x, which we know is the square root of the inner product of r of x with itself. So according to that, that's going to be the square root, and then we'll have to integrate from negative 1 to 1, square root 7 over 2 x cubed times square root 7 over 2 x cubed dx. Okay. Then a little bit messy, but you can sort of see that when we multiply these square roots, that'll drop out. So it looks like we get the square root integral negative 1 to 1, 7 halves x to the 6 dx. Then we'll just pull this over to here. That should be the square root. When we integrate that, looks like we get 1/2 x to the 7th, evaluated from negative 1 to 1, which looks like we get the 1/2 minus negative 1/2 when we plug those in. Of course, again, when we plug in negative 1, since that's an odd exponent, it actually will be negative. And looks like then we should get square root of 1, which is 1. So the norm, or the magnitude of r of x, is equal to 1. Now, that's sort of interesting, because what that basically tells us is that this weird-looking polynomial, r of x equals square root of 7 halves x cubed, is actually a unit vector in this inner product space. Remember, a unit vector, if you generalize that concept from geometry, is something that has a unit length. Well, what we're saying here is that this guy, at least in the inner product we defined, that integral from negative 1 to 1, this guy would be the equivalent of a unit vector, because his magnitude, or his norm, is only equal to 1. That's also going to be something that we're going to be exploring a lot in the next section. Not only are we going to be generalizing the concept of being orthogonal, we're going to be generalizing the concept of being a unit vector, right? A unit vector geometrically is just one that has a unit length. But now that we can talk about inner products for any vector space, we can talk about what is a unit vector in any inner product space. Okay. Well, at this point, we've sort of talked about some standard inner product for Rn, even though there's many other ones, but we talked about one for Rn. We now have talked about a whole sort of class of inner products that can be used for the polynomial spaces or the function spaces. Let's talk about an inner product that can be used on the space of matrices, since that's sort of our other big sort of vector space we keep encountering. Now, this one we will actually go through and prove really does constitute an inner product space, so that you guys can sort of see that process as well. Okay, so let's consider the vector space V equals the 3x2 matrices, and let's let A and B be matrices, right? Then we're going to define this potential inner product. We don't know it is one yet, because that's what we're actually going to prove in this example. But we're going to define this operation that the inner product of A and B is the trace of A transpose times B. Now, this is a really sort of weird operation, so before we get into it, let's just talk about some of its features here. So, since A and B are 3x2 matrices, it might not even make sense to talk about the trace. But let's think about what this operation does here. This is matrix multiplication. So, if A is 3x2, the transpose is going to be 2x3. So we're going to be taking a 2x3 and multiplying by a 3x2, which means that the result is going to be 2x2. That means that the result of A transpose in B is going to be a square matrix, which means that the trace, the sum of the diagonal elements, will make sense. So that's why it sort of looks a little weirdly defined, because otherwise that trace wouldn't even make sense. Think about also this, the trace is the sum of the diagonal elements, so the trace is guaranteed just to be a scalar value, which is what's supposed to happen when you do an inner product. Okay, so the first thing we're going to do is try to prove that this defines a valid inner product. To help you guys, though, let's just do a quick sort of example with some matrices to make sure we understand what this inner product is really saying. So I don't know, let's just for fun, let's let A be maybe this guy, 1, 2, 0, 1, 3, 1. And let's let B also got to be a 3x2, so maybe 0, 1, 1, 0, 1, 1. Okay. So if, according to this, if we were to go ahead and do this operation, what we would need to do is we would need to take the trace of the product of the transpose of this times this. So we'd write out the transpose of that, 1, 2, 0, 1, 3, 1. And then we'd be multiplying by 0, 1, 1, 0, 1, 1. And again, we're just doing this little example here to make sure we understand this operation before we try to prove some things about it. Not necessary, but maybe a good habit. So then this would be the trace. Let's go ahead and actually do this. Notice that this row times column will make sense. So, and again, because this guy here is 2 by 3 and this guy is 3 by 2, we expect the result to be 2 by 2 here. So this row times this column looks like we're going to get 0 and 0 and 3. So we're going to get 3 there. And then we're going to take this row times this column, which we're going to get 1 and 0 and 3. So that sounds like 4. Then this row times this column, so 0, 1, and 1. So that sounds like 2. And then finally, this guy times this. So it looks like we're going to get 2 and 0 and 1. So that looks like we're going to get 3 there. Then, of course, for the trace, we actually could have just skipped calculating these guys because the trace is just the sum of the diagonals. That would be 3 plus 3, which is going to be equal to 6 there. So what we got there is we got that the inner product came out as 6, or what we think is going to be an inner product. Okay, so hopefully that shows you guys that this operation sort of makes sense. Now we're going to actually try to prove that it is a true inner product. So, proof. So we need to show the 4 properties hold. So in some ways, this is going to sort of feel familiar to like when you guys were first learning about vector spaces and you needed to show those 10 axioms held for being a vector space, or when you guys first learned about subspaces and you had to show that those 2 properties, the closure properties, held. Now when we're trying to show something is an inner product, we've got to show these 4 properties hold. So let's go ahead and let's let A, B, and C be matrices. So these M3 by 2, right? That's what we're working in here, 3 by 2. Yeah, we can say this way, be 3 by 2 matrices. Okay. So the first property we need to show is we need to show that A with A is guaranteed to be greater than or equal to 0, and A with A equals 0 implies that A equals 0. So in other words, we've got to show 2 things here. We've got to show that the inner product of anything with itself is guaranteed to always be non-negative, and we need to show that the inner product of something when it equals 0, if it equals 0 with itself, that means it actually is the 0 vector. In this case, of course, this would be the 0 vector in M3 of 2, which is all the 0 elements. Okay, so let's go ahead and do this. So let's look at A, and let's think about what that actually would be. If we give A some actual elements here, it would look sort of like A11, A12, A21, A22, A31, A32, and then of course with itself, so A11, A12, A21, A22, A31, A32. Okay. Now, according to the operation, what we need to do is take the transpose of this, multiply it with this, and then take the trace. So this will be the trace of the transpose, which looks like A11, A12, A21, A22, A31, A32, times A11, A12, A21, A22, A31, A32. All right, so let's go ahead and take a look at that. That's going to be the trace of some square matrix. So this row times this column looks like we're going to get like A11 squared plus A21 squared plus A31 squared. Then we should do this row times this column, but I'm going to skip it because it's going to be this element up here, which is not going to contribute to the trace. So I will just write that it is some whatever up here. Same thing with this guy down here. I'll skip this because this times this, I mean, it's an interesting element, but it's not going to contribute to the trace. So the last one I really need to care about is this times this, which looks like it's going to be A12 squared plus A22 squared plus A32 squared. And that means that the trace is actually going to be A11 squared plus A21 squared plus A31 squared plus A12 squared plus A22 squared plus A32 squared. Now, this is a sum of a bunch of squares of different values. that for sure is guaranteed to be greater than or equal to 0. So we've shown the first part of what we needed to show for property 1, that the inner product of a matrix, in this case with itself, under this potential inner product is guaranteed to be non-negative. Now let's assume this thing actually is 0 and show that that implies that A must actually be the 0 matrix. So we'll go ahead and do that on the next page here. So now assume that the inner product of A with A, which we know is actually A11 squared plus, what order did we write it in? A21 and A31. A21 squared plus A31 squared plus A12 squared plus A22 squared plus A32 squared equals 0. Okay? Now, so we're saying this sum of squares is equal to 0. Well, we know that each of these things has got to be positive, right? Or equal to 0. So if they sum up to 0, that means each of them individually needs to be 0. So since each square is greater than or equal to 0, this implies that A11 equals A21 equals A31 equals A12 equals A22 equals A32 are all 0. The only way you can sum up a bunch of squares and get 0 is if they're all 0 already. So this means A equals 0. Check. So in other words, what we've just shown is that the first property of the inner product holds. The inner product of a matrix with itself under this operation is always guaranteed to be non-negative, and the only way that the inner product of a matrix with itself will be 0 is if that matrix is actually the 0 matrix. So that's one of the 4 properties. That's always the longest property to show. The other one should be a bit quicker. Okay, so now let's go on to 2. We need to show that this thing is commutative, that the inner product of A and B is the same as B and A. Now, I will just sort of say, if we look back, we could do the same approach that we just did here. We could define A and B in terms of elements and then just sort of work through all this stuff. But notice that, we have this nice sort of closed form here, right? This nice clever way of writing a trace of A transpose B. Let's see if we can just use some properties of trace and matrices to prove this guy. So we'll try this in a little bit of a different style. So let's go ahead and talk about what the inner product of A and B is. Technically, that's defined as the trace of A transpose B. Okay. Now, what I'm going to do is I want to sort of note that this is the same, right? Remember that if you're taking the trace of something, the trace of a matrix is equal to the trace of the transpose of that matrix. So this is equal to the trace of the transpose of this. How do I know that? Well, what is the trace? Well, if you can remember that, it's the sum of the diagonal elements. So taking the transpose isn't going to change the trace because the diagonal elements won't move. But now what is the trace of A transpose B? Well, we know that when transpose distributes over multiplication, it distributes onto each and reverses the order. So this would be the trace of B transpose, A transpose, transpose. But what is the transpose of the transpose? Well, we know that that is just the original matrix. So this is trace of B transpose A. But the trace of B transpose A, that's just the definition of the inner product of B and A. Right? You take the transpose of the first one and multiply it by the second and take the trace. That's the inner product we defined. So there we go. We did it. Could you do this using elements? Sure. If you guys want on your own, define A to be A11, A12, A21, A22, A31, A32, B in the same manner, and you can just manually show this. It'll be a bit messier because there'll be all these elements all over the place, but you can show it. Okay, the third thing we need to show is we need to show that Ka inner product with B is the same as K inner product A and B. So let's try the same thing. Let's actually just try to use this sort of condensed definition. So this would be the trace of Ka transpose times B. Now, of course, the transpose is a matrix operation, so we can just bring the K outside. So this is trace Ka transpose B. Right? K is just a constant there. And of course, right, if you're multiplying this matrix by k, you're multiplying every element, specifically every element on the diagonal. So when you do the trace, you can factor that k out. And actually, we proved that way back when we first introduced the trace. So this is k times the trace of A transpose B, which of course is just equal to k inner product A and B, because this is the definition that we define for this inner product. So there we go. We showed that you can factor the constant out. Again, if you don't like this proof, you can go ahead and use elements and prove it a little bit more messily, but you can show it that way as well. All right, for property 4, we need to show that if we have something like A plus B inner product with C, that's the same as doing A inner product with C plus B inner product with C. So we'll try the same sort of approach. A plus B inner product with C is the trace of A plus B transpose times C. How does transpose work with addition? Well, it just distributes onto each one individually. That's a property we showed about the transpose. So this would be A transpose plus B transpose times C. Then this is matrix multiplication. So as long as we're careful about the side it goes on, it does distribute. So this would be trace of A transpose C plus B transpose C. And how does trace work with addition? Well, the trace is the sum of the diagonal elements. So if you sum two matrices, it doesn't matter if you sum them as matrices and then take the trace, or take the trace of each one individually and add that up. So we can take the trace of A transpose C plus the trace of B transpose C. But of course, trace of A transpose C, that's actually the definition of A inner product with C, plus, well, this guy right here, that's our definition of B inner product with C. So we've just shown that the inner product of A plus B with C is the same as the inner product of A and C plus the inner product of B and C. So this really does mean that this inner product, AB equals trace of A transpose B, is a valid inner product. Okay. So at this point, if you think about everything we've sort of done in this video, we defined a standard inner product for Rn. There are many other ones for Rn, and some of the suggested exercises investigate that, but we defined a standard inner product for Rn. We saw a whole family of inner products based on integration for vector spaces that involve functions. And now you guys have seen a inner product. Again, there's many other inner products out there, but this is one example inner product for how to have an inner product defined for matrices. So we've now managed to extend the concept of the dot product from something that just made sense sort of geometrically to something that makes sense for any vector space. In the next video, we'll be moving into section 5.2 and be extending the concepts of orthogonality and being a unit vector to any inner product space.